In this problem, I'm going to look at the electric field due to a uniform disk of charge. I've made a sketch of it here in 3 dimensions. It's tough to see, so I'd spend a little bit of time looking at the sketch. I've got a couple of critical dimensions. Z is the difference that point P is away from the plane of the disk. The plane of the disk is in the XY plane, and Z projects away from that plane. This is very similar and in fact, closely related to the ring of charge problem that has previously been screencasted. We also know that there's some symmetry at point P. All the electric fields in the there's electric field components due to all this different plane of charge in both the X and the Y plane, but the components cancel out. And so due to that symmetry, I'm just going to be left with an electric field in the Z direction. It's also going into and out of the screen, which would be that X dimension as drawn in this way. The strategy is I've darkened one of these rings. So I'm going to take a bunch of these rings, and we're going to only look at the electric field due to one of the rings. And we're going to realize that next to this ring, there's another ring that goes around this origin. And if we were to add those two pieces together and add the next piece together, this is a classic application of integration. And so you just add up all the electric fields due to the different rings, and I would have the electric field due to the disk. So that means that I'm going to start with the expression from the electric field due to a ring that was previously done. Before I do that, I want to say that we're going to introduce this new lowercase sigma, which is going to be area charge density. It's going to be the charge per unit area. Generally speaking, it's going to be the charge on the disk over the area of the disk, which is pi capital R squared. This would be a good time now to say that capital R specifically is the radius of the entire disk, and lowercase r would be the distance or the radius to one of the rings that we're inspecting. So we need to separate capital R from little r. I also need to develop another expression, and perhaps the most important one for area charge density, and that is the charge on one of the rings is going, the charge on one of the rings we can call dq, and the area on one of the rings is going to be equal to the circumference of the ring times the thickness of the ring, where the thickness of the ring I can call dr. And so therefore I can say 2 pi lowercase r dr is the area of one of those rings, albeit very thin rings, nonetheless the area. And so therefore, a critical expression that I'm going to use and ultimately substitute with is dq is going to be equal to sigma, the density, the area charge density, times 2 pi r dr. Okay, let's go ahead and start by suggesting then that the electric field component in the z direction is going to be equal to 1 over 4 pi epsilon naught times z times dq, z times dq, the little bit of charge, over z squared plus r squared to the 3 halves. Now, everything that I wrote here on this first line is the final step of the ring of charge, and therefore I can say that that would just be one of the small parts of the electric field due to one of the rings. So again, everything that I've written comes from a previous derivation that I've shown. This is the contribution of this particular ring to the electric field over here at point P. So now I'm ready to kind of make this substitution that I alluded to earlier. We're going to substitute that for dq. And so the next step is pretty straightforward. The differential of the electric field in the z direction is equal to 1 over 4 pi epsilon naught times z times dq, which I can now write as sigma 2 pi r dr. And in the denominator, I have z squared plus r squared to the 3 halves. And now I'm ready to integrate. I'm ready to integrate both sides and say if I add all of these things up together between r equals 0 and r equals capital R, I'll have the total of all of the electric field contributions to each individual ring. So on the left-hand side, I just get the Z component of the electric field now that I've added them all up together. Over here in the denominator, I still get 4 pi epsilon naught, but now I'm going to pull out constants. Z is a constant, so I'm going to pull that out. Sigma is a constant, that's not changing. I'm also going to pull out 2 pi, and I'm left with R dr over Z squared plus R squared raised to the 3/2. And then I'm going to, I haven't dealt with the integral yet. I have R equals 0 and R equals capital R. I can make a substitution on the left, a reduction, the 2 and the 4, and the pi. That leaves me a 2 in the denominator. So let's go ahead and do that. And now I'm stuck with this integration on the right-hand side, and this is going to be a U-substitution problem, where U is going to be equal to Z squared plus R squared, and du is going to be equal to 2R dr. The problem is I'm almost in that form here. I could do that, but I need a 2 in the numerator. So I'm just going to put 1 there to make my integration go well. The problem is that I would change the value of this, so I need to put another 2 in the denominator so that what I've really done is just multiply this by 2 over 2 and haven't changed its value. So now my next step is the Z component of the electric field is equal to Z times sigma over 4 epsilon naught, and I get on the right-hand side, after I integrate that, I get -2 over u to the 1/2, which I now need to evaluate between my upper and lower limits of integration, which used to be 0 and r, but now when capital R, when little r is 0, that means that this expression is just going to be equal to Z squared. So my lower limit needs to get adjusted, and my upper limit becomes Z squared plus R squared. Because of that U substitution, I changed my limits of integration. Okay, so now that I've done that, I have to evaluate this thing. This hasn't changed. I still get Z times sigma over 4 epsilon naught, and then I'm going to get -2 over Z squared plus R squared to the 1/2. And then I'm going to subtract that from -2 over Z. I guess I made that a little long. So let me get rid of that. And now that I've done that, now technically I'm multiplying my coefficient here times that entire thing. So let's go ahead and evaluate that. I get the Z component of the electric field, this hasn't changed, is equal to Z sigma over 4 epsilon naught. And now I have to get a little creative. I'm going to factor out the 2. And I get in here, I get 1 over Z minus 1 over Z squared plus R squared to the 1/2. And so I get a 2 out here, and we can see that the 2 and the 4 are going to interact with each other here, and I can reduce that to just a 2. And so now I get the Z component of the electric field is equal to Z times sigma over 2 epsilon naught. And then this next piece is a bit tricky. I'm going to factor out a 1 over Z. And so I'll do this in a different color. I get, if I factor out a 1 over Z out of this part, I get in the parentheses, I get a 1 minus Z over Z squared plus R squared to the 1/2. It's a little tricky, but if you look at it, it's something that you can follow. Now the Z's cancel out, that Z and that Z cancel out, and I can effectively finish this expression. Let me go ahead and write this over here. The Z component of the electric field due to the disk is equal to sigma over 2 epsilon naught times 1 minus z over z squared plus r squared to the 1/2. And I'll just write that as a square root sign. And that is my finishing point. So now I have an expression for the electric field due to a uniform disk of charge. One application of problems with a disk of charge would be imagining that the disk extended out to infinity. And this type of a problem would involve a limit. And so I can say, therefore, that the limit as r approaches infinity of that expression, we can see that z doesn't matter, and it becomes 1 minus z over r. So let me write this out. I get sigma over 2 epsilon naught, and in here I get 1 minus z over z squared plus r squared square root. And when I do problems like this, we can see that the z doesn't matter. So we're going to ignore this. We're going to say that this is relatively small when r is quite large. This whole fraction, as r gets larger, closer and closer to infinity, this thing approaches the number 1, because it's 1 minus this tiny little amount if r is huge. It'd be 1 minus z over r, where r is approaching infinity. And so therefore I can say that it's just sigma over 2 epsilon naught. So this arrives at sigma over 2 epsilon naught if r approaches infinity. And I could say that this expression describes the electric field due to an infinite plane of charge.